Hi guys, so we've gone about as far as we can with the finite element method for truss frames without employing any angles of any of the beams. So things were a little bit easy relatively for the problem that I assigned you as homework, because each of those elements was aligned with the global coordinate system. Okay, and what do I mean by aligned? I mean that in the problems we've done so far, we've looked at elements in a straight line. So an element can extend in a direction that enables us to easily tie up an elemental nodal extension, Q1 or Q2, into any Q from Q1 through to Qn, where Qn is the number of nodes in our structure. Even if for a relatively simple problem, the one that we're going to solve in this class today, and let's say we've got, let's need to make sure I'm drawing the correct diagram. Let's say we've got a structure that's got two built-ins. Let's draw that line slightly better. Two built-ins, and we're going to call this node A, B, and C. So we've got element 1 and element 2. Now, even in this relatively simple problem, we can't do that because element 1 extends in this direction, element 2 extends in this direction. So these two elements, their deformations are not aligned at this point. So if we were to look at this part here, let's just zoom in there. Then if we were using the same methodology that we had previously, this direction here would be Q2 of element 2. And this direction here would be Q2 of element 1. So they're not aligned in that direction. So what do we say is Q for node C in this case? Okay, so we don't know, there's no easy way to define QC. Okay, because for example, if I was saying this was my QC here, I would be able to easily say that Q22 is QC. I couldn't very easily say what Q21 is by contrast to QC. And the same if I'd said QC was in this direction, Q21 would be equal to QC, but I couldn't easily relate Q2 in that sense. Q22 rather. So we need a means to account for how we can make this transformation. And the problem arises is because we've got different angular deflections. So not different angular deflections, different angular orientations in this problem. So we've got theta 1, which is the angular orientation of element 1, and we've got theta 2, which is the angular orientation of element 2. So in order to be able to solve this problem, we need a generalized means to account for a transformation from local to global coordinates for elements that have some inclination angle to the global reference frame. Okay, so in order to proceed with the development of this method, we need a means that can account for two things. One is the angular orientation of each element, and that's what we spoke about in the diagram over there. Second one, xy. We've got two displacements of interest, and what do I mean by that? Well, hopefully you can appreciate that if I were to apply a force at node C, this whole node would probably move down, maybe to the right somewhat in this object, which means we need to be able to define nodal displacements in some form of global reference system. So previously we only had Q, which was was a generalized displacement. We now need to be able to define both vertical and horizontal displacements, y and x correspondingly, for our problem. So we're going to look at a method how we can apply a transformation from local to global for a single element that's at some arbitrary angle of inclination, and then we're going to apply it for this problem here. We're going to do it all by hand, and then we're going to say, guys, that was pretty difficult to do by hand even for a simple problem like this, so we're going to come up with a general means, and that's what we're going to be moving on to next week. But today we're going through this problem, and we're going to produce the KQ equals P setup for this problem. We're not going to solve it because you guys already know how to do that. But we're going to do KQ equals P for this. Okay, so let's make a new slide. That's probably easiest. So we're going to draw a generalized element at some arbitrary orientation in isolation. So we're drawing it on its own and looking at what happens. So elements go between two nodes. Okay, and I'm going to draw on uppercase X and uppercase Y. So this is my element. This is its orientation angle. These are our global coordinates. And then this would be its element 1, sorry, it's node 1 and it's node 2. Elements go from node 1 to node 2. So let's think about if this were in a structure, it could be deformed, it's going to extend, and it might sort of, each node could move both along the axis and could also move normal to its principal axis. So this node could move along and up. This node could also move along and up. So we give those two displacements, we give them symbols u and v. Okay, u and v are normally what we use for velocities in later courses, but they just generally are a name for another displacement that we define aligned with x and y. Okay, but these are then going to be the deformations of this element, and the displacements, I'm going to draw them in a moment, that occur locally. So I'm going to copy this diagram. We recognize that in a real structure, each node may be displaced So we're going to call these lowercase u and v. U is the amount that a node moves in the direction along the principal axis of our element. V is the amount that a node might move in a direction normal to that. So we're just going to redraw our problem here. So I've still got global y, global x. Let's draw my elements here. So it's node 1 and node 2. Still at angle theta. We're going to say the element, this is original. Thanks, let's, just because I don't want to overwrite what I'm about to do. So we'll say that I've got the original node, looks like this. Let's write that word with all of the letters in it. Original. So this is the undisturbed element. I'm then going to disturb it. I'm going to move this element. So we'll say it's moved somewhere like this. Okay, so this is my angle here, theta. My element has moved some amount, so this node has moved some distance along the principal axis, some u and some v up. This has moved some u and some v down. Okay, I'm going to go back to this diagram, don't worry. So we make the assumption that each node may move by u and v, as in the diagram above. These are not the same for each node. And what do I mean by that? I mean u1 is not equal to u2, v1 is not equal to v2. Okay, so each node can move slightly different. This is, I mean, they can be equal. I'm just saying here they're not the same. Okay, we could have an element that's perfectly displaced, and that would mean that these were true, but in general these are not the same. We also then further make the assumption that helps us simplify the mathematics is that these displacements are small enough that theta remains unchanged. So in this example that I've just drawn, I've obviously drawn quite a large displacement, but actually we're talking about a small displacement. So let's draw these displacements on here. We've got the amounts that node 1 has moved in an axis aligned with the elements would be u1. And this here would be u2. This is v2. And this is v1. Okay, so our element is this node moves along and up, this node moves along and down. Okay, so we can hopefully appreciate that there is going to be some relationship between these local u1 and v1 and these local u2 and v2 and some global displacements in the xy reference frame, and it's only going to be related by the displacement, sorry, the orientation angle, theta. Okay, so we could do what's called an Euler Transform to determine this relationship, but I'm just going to give you the matrix because I don't want to make your heads explode at this crucial stage of your third year. So we're going to then define a relationship that takes us from these displacements to some form of global displacement. We need to introduce some new nomenclature. So previously we used lowercase to define local. Okay, so this would be, for example, Q1, F1, etc. Okay, and if we wanted to distinguish between different elements, okay, so we then use the superscript to denote some form of element number. So this would be Q11, F12, for example. This says node 1 of element 1. Okay, and this means this is just a pure local, this means the first node that it's connected to for element 1. Okay, this would be similarly node 1, element 2. Now, if we go to this problem here, we're going to want to go from sort of some form of local coordinates. So we've got u1, v1, u2, and v2, which are defined as lower cases. So these are all just, say, for element 1 here. We'd have u11, v11, u21, and v21. So that's subscript 2, superscript 1 for this element. We're then going to want to be able to sort of convert these somehow to A's, B's, and C's for this problem. So we're going to need to do this in 2 steps, okay? Because we previously, when we were going from local to global, we were just saying, okay, well, we know that everything's aligned in the same direction. Now we've got to do things in 2 steps. So now it's not simply a problem of working out which displacement corresponds to which local displacement corresponds to which global displacement. We have to do a transformation as well. So previously it was a single step process saying Q11 was equal to, say, uppercase Q1, and F12 was part of uppercase F1. We now need to actually transform them into a different coordinate system first. So previously it was a case of determining what we'll say as correspondence. And I'll say in brackets here, e.g. Q11 was equal to Q1, because now we have to do some form of transformation as well. And what do I mean by transformation? Well, this accounts for the angular orientation. Okay, so in order to do this, we're going to introduce some, not really new nomenclature, we're just going to introduce some new steps. So we're going to have 3 sets of coordinates for this problem. So I'm going to really exaggerate some of these here. Let's say let me see if this phone call is anything important. I doubt it is. Hello, Harry Smith speaking. No. Okay. It's trouble when you're applying for jobs, you have to answer phone calls that you know are obviously spam. Okay, so we're going to define three sets of coordinates. So this is my elements. Let's say I've got nodes 1 and 2, and let's call this element 1. Let's not draw that in blue, let's draw this in green. Okay. In fact, let's just draw this in general. Let's say it's element E, okay, where E is just a number that we can then replace in this. So I'm going to say that this local displacement in a direction normal to my element is lowercase v1 e. And then up here I've got v2e. And very similarly, I've got u2e, and I'm going to draw this slightly displaced. I'm going to draw u1e. Okay, we can hopefully see that this axis system needs to be rotated through the angle theta. Okay, and the angle theta is simply defined by the angular orientation of the elements. So this then takes us into a set of global coordinates that still only correspond to this element. If we just were to rotate these through here, then we'd end up with a new set of coordinates. So let's draw these in blue. Let's say these are, I don't really have names for these, but let's say we've got local coordinates. In purple, we're going to draw some transformed coordinates. So these are then global coordinates that are only relevant for this element. Okay, let's draw these on here. Am I going to have to overwrite this one annoyingly? Okay, so if I was to just rotate each of these axes here, okay, and I was to define two new coordinates or two new displacements that were aligned with the global x and y, then this would be uppercase u2e, and this would be uppercase v2e. This would be uppercase u1e, and this one would be uppercase v1e. So these are transformed coordinates. So for example, u1e, the fact that it's an uppercase u1, so an uppercase u means it's a displacement aligned with the global x. Okay, the fact that it says node 1 down there, this just means the first elements, so the first node corresponding to the eth element. Okay, E could just be a number. It could be element 1, element 2, element 3, or so on. I just put E there for this sort of general case. So we need a transformation that takes us from local to global coordinates. And whoever takes you for aircraft flight mechanics next year better teach you Euler Transforms properly. I was taught them incorrectly as an undergrad, so it's been a bugbear of mine. I'm not going to do an Euler Transform here. If you want to look at one of the videos, I put a little link in my accompanying notes. So I'll put a link on YouTube of how you do an Euler Transform, because we have to do them a lot for flight mechanics, but I'm just going to give you the transformation here, okay? So we'll say that, let's just say we're going to do a transformation of this here. Okay, so we want to take v1e to v1e and u1e to the bit that I overwrote round here, okay? This is applied at each node and converts from those local displacements that are actually just defined in terms of elongation and then this other deformation that's sort of just normal to that deformation to deformations that are still just pertinent for those nodes 1 and 2 of that element, but are then aligned with the global x and y of our whole coordinate system. So we can say that u1e and in fact, because this is only in 2 dimensions, this is a much easier transform to do. So this matrix here gives us local deformations of node 1, and this one here gives us deformations in the global reference frame of node 2. I think I said node 2 there, so it should still be node 1, okay? So we've got local deformations of node 1, so these are lowercase u, lowercase 2. That's a mistake there, that's why I may be confusing this. These are all just corresponding to, that's bugger, sorry guys. Let's be really clear here, okay? That was a silly mistake. This is v1e, okay? So let's make sure that's a lowercase v as well. Okay, so let's be really clear here. I've got lowercase u1e, lowercase v1e, uppercase u1e, uppercase v1e. So everything we've done here just corresponds to this single node here. Okay, it doesn't say anything about this one yet, but thank the matrix to that node as well. And we end up with okay, and hopefully we can see that we've now got a means to translate these two. We could also just, if we wanted to go the other way, if we wanted to go from u1 uppercase to u1 lowercase, we just take the transpose in this matrix, and since it's orthogonal, it's just equal to we take the inverse, and since it's orthogonal, we just take the transpose of this matrix. Okay, so we've now got this setup that helps us define the relationship between global displacements, even though we've still got these set up just as 1 and 2. So this would be for this first element. We'd do this, for example, we'd go, where's my problem? We'd do this for this element, and we'd end up with a way of converting displacements lowercase u1 and v1 for element 1 into uppercase u1 and v1 for element 1, and we do the same here. We get a means of translating lowercase u2 and v2 for element 1 into uppercase u2 and v2 for element 1. And all that means is we've just taken them from this local coordinate system here, translated them. Local coordinate system, and translated them here. Okay? So we've now come up with a formulation that enables us to do this, but we've still got things in this local reference system. We're going to figure out a means of translating that a little bit. Okay? Now, the one that we care about for determining constitutive relationships is u1 and u2. Okay, let's think about why that is. They're only useful for us setting up the problem. Now, when we defined our spring problem, we had two displacements we cared about. We had Q2 and Q1. And we said that the total elongation of the spring, delta was equal to Q2 minus Q1. If I also, for this problem, had happened to have drawn on V1 and V2, we'll find they didn't play a part in defining this deformation. So they don't form part of the constitutive relationships, so we don't actually end up using them to formulate our stiffness matrix, okay? So for uni-axial two force members, okay, maybe let's not say unit 4, just for a two force member, i.e. a spring, or for a truss bar, a truss element, then all we care about is those displacements here. So we called them Q when we were looking at springs. These would actually be U2 and U1 for this case. So the total elongation of the elements is just going to be, for us now, U2 minus U1. Let's say elongation of any element, because we're going to need to do this for multiple elements, so I'm going to put a superscript E here. It's going to be equal here we go, U2 minus U1. That is, the elongation is a function of those local displacements. And not those global. Well, it is a function of those global ones, but it's only a function of those global ones because we know how to transform them from global ones through to local ones, okay? So we could now take these expressions up here and we can come up with formulations for U2 and U1 as a function of these global displacements. So we may rewrite the above as a delta E, and it was minus U2E. So let's have a look at what U2E would be for our problem. Okay, U2E is going to be cosine theta multiplied by uppercase U2E plus sine theta multiplied by V2E. So let's write these down. Uppercase U2E multiplied by cosine theta plus V2E multiplied by sine theta. Okay, so this is just what was previously U2. Okay, I then need to minus from this, I need to subtract from it U1E. And we can probably see very similarly, it's U1E, it's going to be cosine theta multiplied by U1E, sine theta multiplied by V1E. So I need to subtract both of those terms. Okay, and we can then collect these cosines because we've got two things multiplied by cosine, two things multiplied by a sine. So we've got okay, so we've now got our displacement of each element as a function of however much each node of an element moves in a direction aligned with global coordinates. Let's call it the elongation. And I've written strain because it's not quite the strain. I need to divide it by the original length for it to become the strain. But we can define the elongation of an element as a function of these are the displacements of each node in global coordinate system. So these are nodal displacements, and we'll say with respect to global x, y. And then the other thing we need is simply theta, and that's just the orientation of that given element. Okay, so our constitutive relationship for an element using Hooke's law . So the tensile force in an element is equal to stiffness of an element multiplied, there we go. And now, since we've defined this delta as something big up there, we defined it as this, we can just take this expression and substitute it in down here. So let's rewrite this. Let me copy this because I'm lazy. Put some brackets around it so it makes mathematical sense. There we go. Okay, so we've now managed to come up with a means to determine the stress-strain relationship or the constitutive relationship for an element based upon these global coordinates. Now we're going to take this and we're going to look at doing a sort of a hand solution to that original problem. Okay, so I'm going to redraw that problem that I haven't got on this page anywhere. It's on the previous page, and we're going to use this expression to help us solve for the whole problem here and come up with kq equals p for this problem. And so the steps are going to be, we're going to draw 3 body diagrams of each node, and we're then going to write in the constitutive relationships for each node, and we're then going to collect them in matrix form. And this is going to be a long problem to do. Okay, so I'm going to fast forward through parts of it because it's going to show that it's a lot of tedium. And hopefully we're going to show that we've demonstrated the need to come up with a means that we can automate this through computing. So let me get my original problem, not that one. Okay, so we've got our problem here. Now we're going to draw 3 body diagrams for each node. So we start out with node A. I'm going to have two reactions here. Let's say FAY and FAX. I've then got some force in here, which is force 1 of element 1, and this is the angle theta 1. Okay, so from here I can get two. We should be happy with doing these relationships now. So we should have FAX plus okay, so we get two relationships for node 1 for horizontal and vertical equilibrium. For node B, I've got F1 of element 2 at theta 2. Got two reactions, FBX and FBY. Okay, so then again, very simply, we can just write let's write this in red to be consistent. FBX plus F12 cosine theta is equal to 0. FBY plus F12 sine theta is equal to 0. So we've done those two. Now we just need to draw node C. Node C is here. I've got I'm not going to draw the angles in. I'm going to leave that to you guys because this diagram's getting a little bit messy. But I'm going to draw these general forces on here, FCX and FCY. These are the forces that must be apparent on this object. So we're going to have I should have had little subscript 2's in here. Sorry, that's theta 2 corresponding to element 2 and theta 1 corresponding to element 1. Okay, so we've now got three sets of equilibrium equations for our problem. And we're going to work out some sort of equivalence here. So let's say that this is my, for some reason I'm going to start at element 2. Let's say I've got element 2 up here. If I was to draw those local displacements, I would have U12, U22, V12, and V22. We then transform them into those uppercase ones that are aligned with global xy, and I would have, I'm not drawing these to scale, we'd have V1 of element 2, U1 of element 2, and up here we would have V2 of element 2, let's not draw a tail to that, U2 of element 2. Now hopefully you guys can see that this element here, this is node B and this is node C. So we can see that V12 is simply equal to VB. Okay, it's going to be equal to the vertical displacement of node B u12 is going to be equal to the horizontal displacement of node B, so we'll call this UB. v22 is equal to the vertical displacement of node C, so we'll call that VC. And u22 is equal to the horizontal displacement of node C, so that is UC. So this is our correspondence now. So we don't have correspondence between lowercase and global coordinates in terms of nodal displacements. We've got a transformation from lowercase local displacements to these elemental displacements in global coordinate systems, and we can then say that these correspond to these nodal displacements. So let's write out our correspondence in full. So we've done this for a single element. Let's do this for element 2. Let's do this for element 1. Why not? So element 1 is in this sort of orientation. This would be u11, u21, v21, v1 correspond to v21, u21, u11, and v11. And hopefully you guys can see, let's draw these in a different color. v11 is equal to VA, this is equal to UA, this is also UC, and this one is VC. So this is where we've got both v21 is equal to VC, as is v22 here. So this is how the whole problem comes together, because we're tying the displacement of these two nodes. We've now got everything we need to set up this as a matrix problem. Let's just write these up in some form of concise form. So we can see the correspondence of element displacements in global coordinates. So this is the transformed ones. So for example, this is u1e, v1e, etc. to the nodal displacements. For this problem, that's simply equal to UA all the way through to VC. We've got 6 displacements, 3 nodes, 2 displacements. They've each got. Okay, so we've now got everything we need to set this up as a matrix equation, because we can now just we can take the, which equations are we going to substitute into? Let me just check. Yes, we've got there we go. So we need to go back to our constitutive relationship. So we've got these here. Okay, we're going to substitute in. Let me just go through 1 second. Let me just check. I want to remind myself what we're substituting into each part here. Yes. Okay. Yes, so we've got the force on each element is defined in terms of the constitutive relationship, which is this one here. So we've got this expression. And we've also got these global displacements, which I haven't written down. Let's write those down actually. We've got u11 is equal to UA, v11 is equal to VA, u12 is equal to UB, v12 is equal to VB, and then we've got these ones that are the same. We've got u21 is equal to u22 is equal to UC, v21 is equal to v22 is equal to VC. So taking these expressions and the expressions that we've got for forces here, we can substitute all of those into all of these 6 expressions. Excuse me. Let's do it. Let's do one of these. Let's do one of these. Let's say we're going to look at this f(a)x here. I'll show you how to do one of these. So we're going to take this one here. Okay, so f1 is equal to this expression here. So we need to take this expression, substitute it into where we had f1 previously. Okay, so let's do that. I'm just copying this from the notes. I noticed it in the accompanying notes. I haven't been careful to always include a subscript with the thetas. Okay, so this is where you need to look and think about what each of these things correspond to. One is. Okay, so this expression here is just my f11, or my f1, and then multiply this again by cosine theta 1. Okay, so I can then replace each of these with the corresponding global nodal displacement. So I can then rewrite this as f(a)x is equal to k1 UC minus UA cosine theta 1 plus VC minus VA multiplied by sine theta 1 multiplied by cosine theta 1. Okay, so I've done that for one of these expressions. We need to do this for the remaining 6. I'm actually going to copy this from the account. In fact, I'm not going to do it because it's just a lot of writing down stuff. There's no point in me going through this. It's already in the accompanying notes. We've done this for one of them. This entire derivation is actually included in the accompanying notes. On page 14 of the accompanying notes, I then substitute this into the remaining 5 expressions and then collect them in matrix form to produce, let me substitute this in. Okay, no easy way to copy that in here. If I'd had time, I would have inverted the colors so it would have shown up. But what we have here, this is then just directly from the accompanying notes. We take the 5 expressions that we've just done in addition to the one that I've done, and we put them in matrix form, and we end up with K, Q equals P for our problem. Okay, so I want you guys to go through that and make sure you've gone through and understand how each of those steps is done. And what we're really going to see is actually this is really difficult to do by hand. Okay, but what we've done is we've come up with a procedure that is actually just following the same steps each time. We're taking local coordinates, we're transforming them somehow, we're looking for correspondence between local coordinates and these global nodal displacements, and we're then formulating a relationship based upon our constitutive relationship up here, and that directly enables us to come up with a bunch of equations that we can then put into matrix form. And this then describes our entire problem. So we're going to look at doing a general case of this next week. We're going to formulate the general case by hand, and we're then going to actually code it up, okay? Because this is going to become far too difficult to do by hand. So what I'm going to do is we're going to try and reproduce this using our coded method, and we're then going to go on to some more complicated problems. Okay, so there's this to do. There's some assigned reading that I've given you on Slack as well. If you've watched up to this lecture, you know there's a homework to be done as well. You guys should be good on everything. ask me questions on Slack and let me know how you're getting on. No review this week. I'll see you all next week. Take care.